So without further ado, I'd like to do a little bit of background on our speaker today. We are very fortunate to have Paul Gross, who is currently a meteorologist at WDIV-TV in Detroit. He's been there since 1983, and he actually is even considered a court witness on meteorological issues. He is an expert in climate change and is viewed as a top communicator on the subject. He has been involved in climate change and speaking with scientists about it for over 30 years now. He's also won a number of Emmys for his weather and climate reporting, and has won a first place award from the Michigan Association of Broadcasters. So we're very fortunate to have Paul today, and he is talking, as you see there, about the scientific truth relative to global warming.
Well, thanks a bunch, Gina, and I am really happy to be part of this ACS presentation series, because meteorology really is chemistry and physics of the atmosphere. And what is climate? Well, it's the long-term trends in the weather. So there is a bit of a natural symbiosis here, and I'm glad that some of you that are watching actually have a science background. Usually when I give these lectures, I'm talking to people with very little in the way of formal science background, and I realize some of you don't have that, but either, just doesn't matter if you have or do not have a science background, you'll get something out of this. And I just want to go through just a couple of things real quick before we get started. Number one, I'm going to use the terms global warming and climate change interchangeably. There are some people that try to make some political inference between the two. There is none. I will use them interchangeably and don't read anything into that. Also, this is a science presentation. There is going to be no politics at all here, and I am not an advocate. And in fact, I do not accept any information from any advocacy groups whatsoever. Everything that I'm showing you here is going to be rigorously verified scientific information, peer-reviewed, and so you can rest assured that everything I'm showing you is pure science. I'm not going to show you even any pictures of suffering wildlife or anything like that. This is just a science presentation. And so again, you'll have to ask questions and start discussion when I'm done with the formal presentation, and I'll stick around as long as you have questions. So don't worry about that. So what we're going to do is I'm going to talk about the science. I'm going to talk about indicators. We're going to talk about impacts of the warming, get into some local stuff. Now, I'm speaking from the vantage point of here in Detroit, but there are local impacts around the nation that people are experiencing, and I'm just going to give you some of the perspective from our area here in Detroit with statistics that I've compiled myself, and just a brief mention about the future. So this is pretty simple stuff here. The greenhouse effect, and in fact, the word greenhouse effect, the phrase has taken on a very significantly negative connotation for years, but in fact, it's actually something that's necessary for life as we know it here on Earth. And the concept is very simple. Our planet is covered with a thin atmosphere with certain gases in it that trap heat. And when you get radiation and energy from the sun, that shines through the atmosphere. Some of it is absorbed, some of it makes it to the surface, some of it escapes back out to space, and some of it is, if you will, trapped. And so the amount that's trapped for us has been perfect for life as we know it here on the planet. Because without atmosphere, if we had no atmosphere at all, our atmosphere would be around zero. So we need this greenhouse effect. We need this atmosphere, aside from breathing, of course, but we need it from a temperature standpoint. But the thing is, and this is a factual statement, humans have actually changed the composition of our planet's atmosphere, and there are ramifications to that. And we'll talk about that, and we'll go through that in a second. But first, this should be no surprise to you. 99% of our atmosphere is nitrogen and oxygen with important trace amounts of greenhouse gases. And the four most important greenhouse gases are water vapor, carbon dioxide, methane, and nitrous oxide. Okay? Even though they're in trace amounts, they have tremendous impact in the trapping of that radiation. This is not recent science. Back in 1863, John Tyndall predicted that doubling of carbon dioxide in our atmosphere would warm the surface of our planet. And in 1895, Svante Arrhenius, he actually went further and calculated that the Arctic would warm by 15 degrees Fahrenheit if carbon dioxide increased by 2 to 3 times. Now, at that time, carbon dioxide in our atmosphere was 295 parts per million. Now we're over 400. And you know what? These guys were right. So anybody that says this is just some recent, some recent scientific effort or something, no, this science was established and started back in the 1800s. All right, a lot of people ask, hasn't the planet warmed in the past? The answer is sure it has. The planet has had very significant warmings in the past. But here's what you need to know. Every single one of those previous warmings was the result of something happening astronomically, okay? You have the eccentricity of our orbit, okay, around the sun. You have the axial tilt, okay? Our planet's tilted roughly 23.5 degrees. Well, that shifts. We have the precession of our axis. In other words, the Earth rotates, but it wobbles like a top. So all of the previous warmings that our planet has experienced has been the result of an astronomical change. None of these three astronomical changes that I'm showing you here has happened at the present time. And by the way, I should also add that these astronomical changes have also called cooling periods in the past as well. But again, none of these changes are happening at the present time. So how do we know what the past was here on the planet? Well, the most important one is up here in the upper left, and those are ice cores. Let me take a minute to explain why those are so important and why they're so vital in terms of our knowing the past climate on the planet. Think about what happens at the poles. It snows, and then the next year it snows on top of that snow, and then the next year it snows on top of that, and that goes on for centuries and eons. So what happens is, over time, as the snow continues to accumulate, what happens is the snow compacts, and then it becomes ice. And trapped in that ice are little air bubbles. And those air bubbles are frozen tombs of air as it existed at the time that that air was in the snow. So scientists drill, you can see these ice cores here, they drill these ice cores, and the further down they drill, the farther back in time that they are going. They then extract that air from those bubbles, and they actually know, scientists know the atmospheric composition going back, and I'm going to show you in a minute a graph going back 800,000 years, and in actuality now, since that graph, since I got that graph, back at least 2 million years, okay? So we know not only the atmospheric composition, but also the climate, the general temperature, the average temperature of our planet, because there's an isotope, deuterium, in the atmosphere that changes based on how warm or cold the planet is. And so based upon how much deuterium is in those little historic air bubbles, they can determine also whether the planet was warmer or colder. So we have what's called a paleoclimatic record going back, it's now, I think it's over a couple of million years now. So we have a really good read on past chemistry in the atmosphere, if you will, and temperature. Now, this is the graph of carbon dioxide going back 800,000 years. And you can see lots of ups and downs. You can see that there is quite a bit of variation here. But notice, in the past, the highest level of carbon dioxide we've had in our atmosphere is about 300 parts per million. Now you look at what happened at the start of the Industrial Revolution, and we are now over 400 parts per million. You can look at this one graph, and you can see that we have changed the composition of our planet's atmosphere. We have not been anywhere close to where we are right now in terms of atmospheric oxide, okay? So this just shows you how important that paleoclimatic record is. We actually know what our past changes in atmospheric chemistry has been. All right, let's take a look at the other gases as well. And this is a much shorter time scale where we have much more detail, because we also have tree rings, we have coral, records and ocean sediment records and things like that. So you have carbon dioxide, methane, and nitrous oxide. And again, you have the start of the Industrial Revolution right here, okay? And you don't have to be a scientist to look at this and say, all right, well, you go back, over the past, period of time here, and it was very, very stable. Then all of a sudden, the Industrial Revolution starts, and you can see those gases dramatically increase in the atmosphere. So yes, it is a factual statement to say that humans have changed the composition of our planet's atmosphere. There are some people that refuse to believe that. They think, how can just people change something so massive as our atmosphere? Well, we've done it. We have changed the composition of our planet's atmosphere. It is 100% fact. All right, this is what I consider to be the most important slide in the entire presentation, and yet we're only in the middle. But I put it in here because this is where it fits. And before I explain the graph itself, let me explain something real quick about climate models. So let's say a scientist or a team of scientists come up with a climate model. You obviously have to come up with a way to determine if the model has any kind of value. So what do? You plug in past data, and you see if the model can replicate what has happened over, say, the past 60 years. Okay? If the model can take the past data and it can pretty accurately show what has just happened in the past 60 years, then you say, all right, the model has some value in telling us about the next 60 years, perhaps, or the next 100 years, or whatever. And so what you have here is a comparison of some of the most reliable computer models. Now, this orange graph, line right here on the graph, that is actual observations, okay? You're going back to about 1880, and you go to the present, and you can see, especially starting in 1960, you can see this very steady, I mean, I know there's year-to-year variation, but listen, if you're a scientist, you know, you see trends here, a very distinct upward trend in temperature here. All right, now this green graph here, this green line, what they did is they averaged the computer models that had everything in them that could possibly force any change on the climate. Things like solar activity, volcanoes, human emissions, things like that. Everything that could possibly cause any kind of forcing on the climate is in those models. And if you notice, those models, this green line, it matches up pretty good with what actual observations are. Now, the blue line, what they did is they reran the climate models, okay? And what they did is they took out one thing. They took out the human added increase of greenhouse gases in the atmosphere. They left everything else in. All they did was take out the human impact. So if you take out the human impact, those climate models, look at this, they've actually projected that there would even been some cooling since 1960, okay? So this is, I call this the smoking gun slide here in the presentation, because people ask, how do we know that there's the human footprint? How do we know that there's the human impact? And this shows you that there is no climate model and there is no scientist that has been able to come up with a way to replicate the heating that has occurred, the warming that has occurred in the past 60 years without the human element. It just can't be done. So that's how we know that there is the human component in all of this. All right, if you're wondering the percentage, the breakdown of those greenhouse gas emissions, well, you can see here on the chart, carbon dioxide is 82% of it. Methane is 10%. You're thinking, oh, it's only 10%. That is very important because methane is a significantly more potent greenhouse gas than carbon dioxide, significantly more. And we're seeing an increase in methane. So methane is something we need to keep an eye on. You have 5% nitrous oxide and 3% fluorinated gas. And if you're wondering where they all come from, well, 80% of it comes from transportation, electricity, and industry. The rest of it, the remaining 20%, is mostly commercial and residential, and also agricultural. Excuse me. And so that's the breakdown of where those greenhouse gases are coming from. All right. If you're a scientist, you know that science isn't necessarily consensus, but policy is based on consensus. And so you should know that 97% of actively publishing climate scientists agree that human-caused climate change is happening. And if you look at the scientific journals, the peer-reviewed journals, 99.9% of the papers published in those peer-reviewed journals find that human-caused climate change is happening. And in fact, I read one of those journal articles, and they said, the authors said, that the number of papers being submitted with any kind of conclusion opposite to this is, quote unquote, vanishingly small, okay? And I equate this to like what happened back in the 1950s when some of the first medical studies started coming out saying that smoking predisposed you to other types of medical maladies and conditions and diseases. Well, at first there were doctors that just didn't believe it. There were some doctors that were actually paid to do TV commercials for cigarette companies. But over a period of time, an overwhelming balance of medical peer-reviewed research basically overwhelmed any opposition to the conclusion that smoking causes these conditions and predisposes you to these diseases and things. Okay? And that's what's happening with climate change. Basically, there was a lot of uncertainty if you go back 30 or 40 years. And listen, I interviewed my first climate scientist in the early 1990s. And even then, they were starting to get confident about this, but there were still uncertainties. Well, now we're closing the gap on a lot of those uncertainties. And most of the climate scientists around the world are in fact, the overwhelming majority are very much in agreement on this. All right, let's get into some indicators. This is global temperatures from this past year. Anything pink or red is a warmer than average year. Anything that's blue is colder than average. So I'll let you take a look at this and tell me what you think the world experienced this past year. Yeah, you don't have to think very hard about that. The world, for the most part, almost everywhere was warm. You can see actually, if you're looking carefully, there is a part here in the central United States that actually was a little bit cooler than average. And there's this. We'll talk more about this later. This is here south of Greenland. We'll talk more about that later. But you can see most of the planet was warm. And that's why I actually prefer the term global warming to climate change, because it is a global warming. I think that's a more specific term. All right, let's look at the 10 hottest year record. In fact, here, let's tell you what, let's focus on the 8 hottest years on record. Let's see, the 8 hottest years on record: 2013, 2014, whoops, I didn't mean to do that. 2015, 2016, 2017, 2018, 2019. So from 2013 to 2019, we had our 8 hottest years on record, and 2000 and 2005 were the other 2 to round out the top 10. So if you had 1 or 2 or even 3 of these years that somehow were significantly warmer than average, you might not think of anything, but the fact that you're seeing this, it shows that there is a warm forcing on our climate. All right, now let's talk about this. You've heard of El Nino. That's when those warmer Pacific waters, the surface waters, are pushed eastward and pool off the west coast of South America. La Nina is the opposite. Those warmer waters are pushed westward. El Nino years are warm years overall for the planet. La Nina years overall are cooler years for the planet. Now, what I want you to see, this goes from 1950 to the present, and well, till a few years ago. This graph was done a few years ago, but I thought it was so significant that I wanted to still keep it in here. Now, these orange bars here, each bar is the average temperature for the planet for that year, okay? The orange bars are El Nino years. The blue bars are La Nina years. And again, La Nina years are cooler than El Nino years. But look what's happening. La Nina years now are actually warmer than El Nino years were just a few decades ago. So we're actually seeing a warming that's actually overcoming the La Nina, the cooling impact of the La Nina. So if anybody tells you that, well, we had this hot year, but yeah, there was an El Nino, well, no, that's not really relevant, because we are overwhelming the impact of the La Nina and the El Nino cycle. The El Ninos are becoming warmer than normal El Nino years, and the La Nina years are becoming warmer than normal cooler years. So it's not just El Nino. All right, another thing to show you consistency. What you have here is a temperature reconstruction. So in other words, it's average temperature for the planet for each year from 1880 to 2014, okay, relative to normals. This is the temperature anomaly. In other words, compared average from 4 different completely independent climate research institutions, and look at the consistency in the lines here. Look at how consistent these lines are. So you're seeing tremendous consistency among the 4 different climate research groups in their reconstruction of the temperature record from 1880 to the present. All right, where is the heat going? Well, this is something that's a surprise to a lot of people, okay? 93% of the excess heat being trapped by those gases in our atmosphere is going into the oceans. 93% of that excess heat is going into the oceans. So think about this. Our planet is 3/4 ocean water. Let's say we were 50% land, 50% ocean. Well, in that case, the land where you and I live would be heating up significantly more than even what we're experiencing now. So we're actually kind of lucky that 3/4 of our planet's surface is ocean water. Those oceans are taking up 93% of the heat right now. Okay, and so that's really important. So the warming could be even, the warming I should say that you and I are experiencing could be significantly more than what we're experiencing if it wasn't for the fact that we had so much ocean on this planet. And speaking of those oceans, the oceans are heating up. Here is the change in sea surface temperature since 1901. Orange and red is warmer and blue is colder. Notice anything? One thing we're going to talk briefly about is this little thing right here. See that little bowling ball south of Greenland? What that could be is cooler ocean surface waters due to the melting of the Greenland ice sheet. That ice, melts, and that water has to drain into the ocean. That's what that could be. And you're thinking, okay, well, that's important because, first of all, keep in mind fresh water and salt water. The ocean's just salt water. That melting ice is fresh water. They have different densities. And so the different densities could change a very important ocean circulation pattern there. Now, you all know, I think you've probably heard of the Gulf Stream. We have warmer temperatures, warmer water temperatures down here, like in the Caribbean, the Gulf, and those flow up the east coast of the U.S. across the Atlantic and toward the United Kingdom. That's why the United Kingdom is so mild, relatively speaking, in the winter compared to like the northern United States or southern Canada at a similar latitude because of that Gulf Stream transporting some of that ocean heat. Okay, so that's by the way, that's called the AMOC, the Atlantic Meridional Oceanic Circulation. And so there is some body of research right now looking into to see if that melting, that change in the density of the water is going to change that AMOC. So those ocean circulation patterns are very important in terms of our overall climate and weather. We already talked about El Nino and La Nina. That's an ocean circulation pattern, the shifting of those warm Pacific Ocean waters. Well, we need to keep an eye on these various ocean circulation patterns because, for example, let's say the AMOC were to break down. I don't think anybody's expecting it to completely fall apart. And in fact, I think that's a very low probability scenario. But that could significantly impact the weather for parts of Northwest Europe here. So that's just another aspect. See, this whole thing with climate change, you have a series of dominoes. When one domino falls, another one falls, then another one falls, and our job is to determine what those dominoes are and their relative importance. And so there's a lot of research going on about these ocean circulation patterns because, again, the oceans are very critical in terms of the overall weather and climate that we get here on the planet. All right, let's look at sea level. This is actually very interesting. So sea level is going back here, and you can see going back, was it 2,000 years? My picture is actually in front of the, I think it's the 1st century, yeah. So on my screen here, the picture is covering the lower left part of the base of the graphic there. So that's about 2,000 years of sea level rise. And yes, there's fluctuation. You see that. But then look at the 20th century. I mean, that is so abnormal compared to what we've seen from a century standpoint over the past 2,000 years. It's extraordinary. But something is very, very important to understand. If you ask somebody who maybe is not familiar with climate science why the sea levels are rising, most people are going to say, well, it's because the poles are melting. That's only partially true. Water, as many of you know, if you're a scientist, you might know this already. Water has a very interesting property. When water warms, it expands. That's called thermal expansion. So just the fact that the oceans are warming, and I've already showed you the oceans are warming, just the fact that the oceans are warming is causing about 1/3 of our sea level rise. Just the fact that the water is getting warmer, it's just, its volume is expanding. And then the rest of it, the other 2/3 or so, is from ice caps, from ice melting, glacial melting. But there's something else to understand. If you, for example, look at the North Pole ice, melting North Pole ice does not affect sea level. That's because that ice is already in the ocean. It has already displaced its volume. So when that ice melts, it doesn't affect sea level. Just like if you take a glass, fill it up with ice water, set it on the counter, the ice melts, but the water doesn't just flow over and make a mess on the counter? It's because the ice has already taken up its volume in the glass. And so it's the same thing with the North Pole ice. Now, the Greenland ice sheet and the Antarctica ice sheet, those are on land. So as those melt, and they are, that water is going into the oceans, and that is contributing to sea level rise. Okay? All right, this is really interesting. This is from satellite imagery. This is North Pole ice. And before I put this in motion, take you from 2000 to the present, the white you see is older ice. Older ice melts much slower than newer ice. Okay, the newer ice, you can see as you get further into the colors of blue, that's newer and newer ice. Okay, so as the pole, oh, why didn't that work? Hold on here, I have to figure out how to make that work. I want to play this. Maybe I have to move. Hold on one second here. We're going to have to move something here. All right, let me move this. And here we go. Let's see if that works. Come on, work. This should play. Hold on. I'm trying. It worked when I tried this earlier. Okay, you know what I'm going to do? I'm going to back up. Here, let's try this again now. Oh, it's not working. Well, I'm sorry. This is supposed to play, and it played when I tried this. Actually, about a half an hour ago, I tried this, and it played, and I don't know why it's not playing right now. But in any event, you would see, if this were able to play, you would see that by the time you get closer to the present, a lot of that, one, the amount of ice is decreasing, but also you'll see a lot of the whites going away and being replaced by that bluer, the newer ice, which means that seasonally that ice will melt much easier. All right, Great Lakes. Again, I'm here in Michigan. Some of you may be in other places around the country, but I've done a lot of, obviously, looking into the impacts on my state. And here, for example, ice cover. Great Lakes freeze over in the winter, or at least partially do, and we're seeing a decrease in Great Lakes ice over the course of the winters, going back to 1973 here. And when you do that, that means you get more lake effect snow, because lake effect snow occurs when you have cold air coming across those relatively warmer waters, and then you dump more snow on the opposite shoreline. And so it seems counterintuitive, but you can actually have more snow in a warmer climate, and that's because we would have more open waters. And there's another thing. With the warming of the planet, we are also seeing an increase in atmospheric humidity. And that's because as you warm up the planet, more ocean water is evaporating into the atmosphere, and that water vapor that you put in the atmosphere is what storms turn into precipitation. So we're seeing an increase in high-end snow events too. But take a look at this. Let's get back to this. Okay, another thing that we look at is before and after comparisons. Now, this is Muir Glacier in Alaska. Look at the picture from 1941. These are taken from the same vantage point. 1941 and 2004. It's just remarkable. The glacier has retreated 7 miles, and its thickness has decreased by a half a mile. And that just happened because you have a couple of warm years. That has to happen over a long period of pronounced warming. Okay, Muir Glacier in Alaska, just extraordinary. I don't know if this is not going to play because the other one didn't play. We can give this a shot. Okay, I'm going to give this a shot here. All right, let's first talk about the distribution of temperature extremes. So if the climate was completely stable and there was no warm or cold forcing, in other words, we were just kind of in a steady state, you would statistically expect an equal number of record heat and record cold. Okay, now on this graph, the records are toward the ends here. Okay, and this area here in the middle, that's kind of what we'll call normal or average. Okay, and then this is colder than average, that's warmer than average. So we're going to try this one, see if this one plays. And for some reason, all of a sudden, well, all right, for some reason, the two animations that I have here are not playing, even though they played when I tested this just a little while ago. But in any event, if I were able to put this in motion, what you would see is the blues and the reds here shifting to the right The red's increasing, the blue's decreasing, and it shows you what has happened. We're seeing more extreme heat, less extreme cold. That doesn't mean we can't get extreme cold. We're just seeing less of it. And the frequencies, you see the frequency shift. I just wish I could show you this animation, but for some reason those are not playing. I'm not sure why. It might have something to do with the fact I'm on Zoom, and maybe that's it. All right, so as I mentioned, we're evaporating more water vapor, water into the atmosphere, and creating more water vapor, or what we call atmospheric humidity, planet-wide, and we're seeing an increase in extreme precipitation events. Here in the United States, the entire country is seeing an increase in the most extreme precipitation events. In the Northeast here, it's 42 to 55%. And then you can see the rest of the country, the increases are more modest, but they are still happening. So we are seeing what I like to call extreme extremes. We're seeing an increase in those higher intensity precipitation events just simply because there is more water vapor that is available to produce precipitation. And that includes snowstorms, by the way. That includes snowstorms. All right, let's talk about tornado outbreaks. And as you all know, just this past weekend, we had a horrific Easter Sunday tornado outbreak down south. Now, what we're looking at here, okay, is the number of the largest tornado outbreaks each year. So in other words, you take the biggest outbreak that happened in any given year, okay, you see the start to the end here, the period of time. We take the biggest outbreak that occurred in any given year, okay, and that number of tornadoes that was in that outbreak is plotted on this graph. And as you can see, there is a definitive upward trend in the number of tornadoes that are occurring in the biggest outbreak every year, okay? Now, in a warmer world, there are some projections that we would see actually fewer tornado days. So in other words, fewer days in which a tornado occurs in the country, but those outbreaks would be worse, okay? So you kind of pick your poison. You have to decide, well, is that good or bad news? Fewer tornado days sounds like good news, but if the days where you have those big outbreaks are worse and more severe, well, is that bad news? You know, is the bad worse than? So you know what I'm saying? I have to decide which news for you. You can see with tornado, at least, that the number of tornadoes and largest outbreaks is increasing. All right, raise your hand if you have allergies. Most people lectures in person, I can't see, but most people, when I give these lectures, I'd say 2/3 of the people raise their hands. Well, what we're seeing is a longer growing season, and a longer growing season means a longer allergy season. And you can see here that we've had a very steady increase in the length of the growing season. And so if you have allergies, you're going to have a longer allergy season in the decades ahead. But wait, the news gets worse. With more carbon dioxide in the atmosphere, plants are producing more pollen. And so we are going to see an increase in the amount of pollen produced per plant over the coming decades as well. And so if you have allergies, and a lot of people have allergies, that means that your allergy season is not only going to get longer, but it's going to get more severe as well. All right, I'm going to get into some local stuff, and I'm focusing on my area, Detroit, but this is applicable to some other places around the country as well. And it just shows you kind of a more granular look at, because they say, they say weather is what you get, climate is what you expect. Okay, well, this is actually talking about, because people ask, well, how will this affect my weather? Well, this is an effect on my area, in the Detroit area. And so what we've got in white here, okay, in white here, this white line is our average temperature, okay, for the whole year. Okay, so you can see, it warms up in the summer and cools off in the fall. Okay, now if significant cuts are made, that's this yellow line. And then this orange line is if emissions are pretty much unchecked. And like, for example, right now in the Detroit area, you can see our average high temperature in the middle of summer is 84 degrees. Well, that average high is going much, much higher, above 90. Whoop, I didn't mean to do that. Sorry. Above 90 degrees in the coming decades. And so by the year 2100 is specifically what this chart is for. And so I mean, this is a real impact. And in fact, I had a climate scientist a number of years ago tell me that if things just go unchecked, that a Southeast Michigan summer by the year 2075 was going to feel like a Southwest Missouri summer does today. So that's a real life weather impact to the warming. All right, I did my own study, okay, and what I did was for 3 decades, I counted the number of temperature records, heat or cold. And it's important to remember you can set 3 different warm records or 3 different cold records in any given day. So let's talk about like heat. You can have a record high, you can have a record for the warmest low temperature, or you can have a record for the highest average temperature for the day. So you can actually set 3 different temperature records in one day, either hot or cold. Okay, so back in the 1990s, that ratio here in the Detroit area was 3-to-1. Now that by itself is unusual, because if you had no forcing on the climate, I'm not saying it would be exactly 1-to-1, but it would be a lot closer to an even number of record highs and record lows. But in the 1990s, that ratio was 3-to-1 in favor of warm records. The next decade, it was 6-to-1. It was 6-to-1 heat records to cold records. And then now we look at the current decade, and yes, the current decade, meteorologically, it ends at the end of this year, okay? I know some people said that we've already started the new decade. No, for meteorologists and for our statistical purposes, the decade ends at the end of this year. We have had 133 warm records, 38 cold records. And keep in mind that I think 24 of those cold records happened in those 2 polar vortex type winters that we had, 2014 and 14-15. Okay, those were 2 very unusual winters, and we had, I think, roughly 24 cold temperature records just in those 2 winters. So if you look at the rest of the rest of the decade, well, that just shows you the skewing toward the warmer climate. One last thing, snow impacts. I told you about the more moisture in the atmosphere means more precipitation, intense precipitation events. Here in the Detroit area, 6 of Detroit's top 15 all-time snowiest winters have occurred since 2002. Look at that. 6 of the top 15 all-time snowiest winters have occurred since 2002. So if we are in the storm path or we're getting the storms are dropping more snow. And so we are seeing snowier winters in those winters where we're in the storm path. So that's just another weather impact that we're seeing here in the Detroit area. All right, we're getting close to the end of this year, by the way, and then we'll open it up to discussion and questions. But hot summer days. This is a simple chart of the number of days with above average summer temperatures. And again, you can see very clearly that there is a very steady upward trend in above average summer days. Okay. And then people are wondering, is any particular season warming more than the others? Well, all the seasons are warming, but look at this. Look at this. Here in Michigan, winter is actually the season that is warming the most, followed by fall, and then spring and summer are both kind of close together there. So just in case you were wondering, the seasons are warming at different rates. All right, last thing I want to talk about is the future. Just a couple of slides here. And what this shows is future warming based upon emissions cuts. So the current path that we are on right now is this line right here, okay? And this line down here is if there were extreme cuts. And so obviously extreme cuts is very difficult to do. Just, it's like some people can just stop smoking cold turkey. Well, we can't just stop using carbon cold turkey. That's just not possible. So obviously our aim is for something, something in the middle here. And really the goal of scientists is to try to stay below 2 degrees Celsius for an average planet warming. A lot of scientists believe that's kind of a threshold, and going above that will then lock us into some types of changes and things that are just very, very undesirable. Just again, a local, the future, this is just really specific numbers to that graph I showed you earlier. Right now in the Detroit area, we average 13 90-degree days every summer. By the year 2100, if things are pretty much left unchecked, we will average 68 90-degree days. in the summer. I mean, think about that. That is just absolutely extraordinary if nothing changes. And by the way, that means also conversely in the winter, fewer nights where we drop below freezing. And people think, well, that's good news, but it's not necessarily good news, because up here in the north, there are certain pests like ticks and things that are killed by those periodic Arctic blasts. If we have milder winters, more of those pests that are a problem here in the warm season, more of those pests are going to survive the overwinter period, and they're going to survive into the next season. So this isn't necessarily all good news. So that's it, really. Carbon dioxide remains in the atmosphere for hundreds to thousands of years, and that locks us into additional future impacts. And we already talked about those impacts, things like sea level rise, extreme heat, heavier rainfall, things like that. So the last thing I want to say before we open it up to questions is that if somebody says we have to stop global warming, that's an extremist point of view, because we're actually past the point of stopping the warming. We cannot stop it. What we should have as a goal, and what the language should be, is that we need to slow the warming. Because if we can slow the warming, we can slow the changes that are happening. And if we can slow those changes, humans can mitigate. Animals can adapt. They can migrate, or they can adapt. So moving forward, I think the language should be we need to slow the warming. And if we can, I think that would be a reasonable goal. And just to kind of finally to tie this all up in a bow, probably the one good thing about this coronavirus pandemic is that you've all learned, well, not you, those of you that are scientists know what this means, but the public in general without a science background has learned what flattening the curve means. We climate communicators, we've been talking about flattening the curve for years. We're talking about trying to slow the warming. That's flattening the curve. That's what we need to do with climate change. And now people are finally kind of understanding what that means. So again, we can't stop the warming, but now you know the science behind what's causing it and what the ramifications are going to be. And again, I think the goal should be, and I think you've seen that it should be, let's slow the warming. So with that, I would love to open it up to questions, discussion, anything you'd like to know.
Well, you can see these questions also. It says, first one is, how does the increase in temperature?
I gotta see, wait, how do I see them? Because I'm trying to see.
I think you just go to Q&A below.
There it is.
Yeah,
there we go.
For you if you can't. You can see that first one.
Yeah.
I also have several. I can't type into Q&A, so I will be asking mine live. Go ahead and answer this first one.
All right. The question is, how increase in temperature affects oceans' ability to trap more carbon dioxide? Will oceans eventually start releasing trapped carbon dioxide to the atmosphere? Yeah, that's called outgassing. And when the oceans are colder, they can absorb more carbon dioxide. But as they continue to warm, they will not be able to absorb as much of that carbon dioxide, and they'll even start outgassing perhaps. But the thing is that as the oceans absorb carbon dioxide, they are becoming more acidic. We are changing the chemistry of the oceans. And so if you are an organism that lives with a shell, okay, those shells are a base. And if you make the ocean more acidic, well, you know what more acid does to a base. And so any organism that lives in the ocean that has a shell could be in for a very tough future if we keep with the carbon dioxide increasing in the atmosphere.
Okay, I have several questions for you, Paul. Maybe you can address how people are taking all these global temperatures. How many places on Earth do they take a temperature? Does it vary depending on the model? You know, there must be places on all the continents where these are taken. Can you comment a little bit about how the people come up with the temperatures to graph?
Yeah, we have a pretty good global temperature network now. And there's an organization called the World Meteorological Organization, or WMO, which is a specialized agency of the United Nations. It's part of the UN. And I've actually been to Geneva, and I've interviewed the past Secretary General of the WMO up in his office in Geneva. And one of their biggest goals is the standardization and the improvement of the temperature record around the planet. And that includes, even in developing nations and places like that. So we have temperature observations all around the planet. There are there are some ocean buoys that also give us temperature data about the ocean water as well. And we even have weather stations at the poles. There are scientific research institutions in Antarctica, for example, like the McMurdo Station, where they are taking regular scientific observations. So we have a pretty good temperature network around the planet. We have a real good handle on the climate that we're seeing today around the planet. I hope that answered the question.
Yes. I don't see any more in there right now, so I'll just go ahead and ask another one. You mentioned that CO2 increases pollen count. Why is that?
Well, carbon dioxide is basically food for plants. I mean, plants take in carbon dioxide and they actually give off oxygen as a byproduct. So that's why you keep hearing people say plant trees. Trees are part of perhaps a planetary solution. It's not the only solution, but if we plant more trees, they're going to take in carbon dioxide. And so with plants that produce pollen, if they are in an atmosphere with more carbon dioxide, they're just going to be growing more robustly and they're going to produce more pollen. So that's why that is. And I see another question just popped in. Excuse me. Now, let's see. With all of this excellent research on climate change and causes, what would you say are the current gaps in our understanding and gaps in research? Well, let's see. One gap is cloud cover, because it takes a real special kind of a climate model that can model the change in cloud cover around the planet. And I'll just say this as something that would make some sense. For example, if you have more water vapor in the atmosphere, perhaps in some places you'll have more cloud cover. Now, if you have more cloud cover and more atmospheric humidity, maybe your daytime highs aren't going to change as much, but the cloud cover would keep the overnight lows much, much warmer. And we're seeing that in some places. We're actually seeing that the global warming is actually more pronounced at night than during the day. That's one thing. Another thing that scientists are trying to get a handle on is aerosols in the atmosphere. And that's a whole nother body of research, because aerosols, like say dark soot, that type of stuff, it can block solar radiation, but also the dark color absorbs solar radiation. So scientists are trying to get a better handle on aerosols in the atmosphere as well.
Okay, I have another question. I've seen some things on the news lately with COVID-19 where they have, there's been some data collected and graphs or diagrams are showing that pollution has actually decreased a lot in places where there's stay-at-home orders because people are getting out, or not getting out. So do you have any comment on that, and how that happens, how much it takes to make a significant decrease, et cetera?
Well, there are two things that are happening as a result of the stay-at-home order in many states. And one is, as you mentioned, people are driving less. And so that's less emissions in the atmosphere. And also we're flying less. So there's a lot less air travel. So from that standpoint, there's less in the way of emissions being put in the atmosphere. And even forgetting about climate for a minute, that just means cleaner air. I don't know a single person that's against cleaner air. But in any event, with planes, for example, okay, as you all know, on some days when you see a plane go across the sky, you see that contrail behind it. And sometimes those contrails kind of spread out and form kind of a long cloud, if you will. It's kind of like a hot dog across the sky. And so with fewer planes, we're seeing fewer contrails and fewer, of those types of clouds. And so that's another impact, and that we're seeing less of that type of cloud cover. But something else that's even more important, you see, in order for us to forecast the weather, okay, we have computer models that depend upon upper air data. Now, at weather stations all around the world at the exact same time twice a day. So here in the Eastern time zone, it's 8 a.m. and 8 p.m. And in England, for example, it's noon and midnight, okay? They launch weather balloons with packages of weather instruments. Those are called radiosondes. And as they float up, they give us a read on things like pressure, temperature, wind, humidity, et cetera, dew point, all of that as it goes up. And all of that is fed into the computer models. But those balloons aren't everywhere. So like, for example, here in Michigan, they launch a balloon in Southeast Michigan. They launch another one, I believe, up in Gaylord, which is, okay, wait, we always have for those of you not from Michigan, we always have our map on us. So here in Southeast Michigan, they launch one. They launch another one way up here, in Gaylord. And you have one over here in Green Bay. And so you see there's space between those. But we also get upper air data from airplanes, from commercial jets, commercial airplanes. And with fewer flights right now, we're getting less of that data. And one thing we're trying to see right now is if we're seeing a bit of a decrease in some of the accuracy of our computer models. And so that's another potential impact that we're looking into right now.
Are you familiar with the book called Drawdown with regard to research where people have talked about taking CO2 out of the atmosphere by 100 top things we can do to remove CO2 from the atmosphere?
I've seen some of the projects going on. People basically taking carbon dioxide out of the atmosphere, and then something called carbon sequestration.
Right.
So what do you do with it then? Well, they talk about burying it, hundreds of feet below the surface in like limestone formations or something. Right. And right now, yes.
Okay.
Taking carbon dioxide out of the atmosphere could be part of the solution. Right now, at least from the last that I've read, it's not cost effective. And they're trying to find ways to do that in a more cost effective way. And if you could, then it would be part of the solution. Yes.
Well, yeah, that is a really interesting book because it does talk about the top ways that you can do it. Then they say things that we can do right now. And the way that book is presented, I'd recommend it for people in the audience because it presents the number of gigatons that would be removed of carbon dioxide removed from the atmosphere by these actions, how much it would cost over a certain period, and how much it would return to the economy after a certain period. So there's a lot of good information there. And yeah. My question, and I guess I don't remember, I haven't read the entire thing, but in the forward they talk about the research methods, et cetera. And I guess my question is, maybe what they're talking about is removing carbon from the atmosphere to stabilize the changes that you're talking about. Do you think it's possible if you remove enough, you can actually decrease temperatures to go in the reverse direction?
Well, I don't know, because you're talking about such a massive amount of carbon dioxide. I don't know if you'll decrease the temperature, but again, the goal is if we can slow the rise or even flatten the curve, that would be massive. That would be huge if we could do that. Like I say, I don't know if we could cool in the next few decades, but if we could at least slow it, that would be really, really important. Okay. And so it's just, and don't forget, remember there's methane and nitrous oxide, that are up there too. But methane is a really big one because even though there's a lot less of it, I think I showed you that it's only 10% of the percentage of greenhouse gases, but methane is significantly more potent as a heat trapping gas than carbon dioxide. So carbon dioxide is the most prevalent greenhouse gas, but let's not forget about methane too. That's a real important one. And we got two more questions that popped in. Should I address those?
Yes, please.
Okay. The first one is, what are your suggestions for helping our members of Congress better understand what's happening to our climate? All right. I told you I don't get into politics here. What I'm going to do, I'm going to explain to you in a non-biased, nonpartisan way why there is a difference in the political parties. Okay. Basically, in order to do something about climate change, that generally involves regulation. Now, Democrats love regulation. Some people would argue they love too much regulation. Now, Republicans don't like regulation. Some would argue they want too little regulation. And so what has happened is on the right side of the aisle, there has been a resistance to doing anything about climate change because that involves regulation, which they don't want. And I'm not taking sides here. I'm just telling you something very factual. Okay. What I wish would happen in Congress is, listen, we pay these people to go to Washington, debate things, and come up with policy that makes life better for us or that protects our nation. That's what they're supposed to do. They're supposed to debate this stuff. But what has happened is the Republicans are trying to discredit the scientists and the science. The science is virtually settled. So if they could accept the science and then go ahead and argue, what do we do about it? Because they're supposed to argue policy. They're supposed to debate policy. So debate, what do we do about it? But just accept what the science is telling us. And here's an analogy I like to use, and this really resonates when I give this lecture in person to groups. Let's say you woke up one morning and you go into the bathroom, you look in the mirror, and you see like a lesion or something on your ear. So you go to your doctor, and your doctor says, you know what, I think you have a melanoma. We better get that taken out right away. And you say to the doctor, no, I want to get 99 other opinions. So I have 100 opinions, and then we'll decide what to do. So you go to 99 other doctors, okay? And of those 100 doctors, 97 of them say, yeah, I think you have a melanoma. We better take that out quickly. And 3 of those doctors say, you know, I think there's enough uncertainty here. Let's wait and see. What would you do? And so that's what I say to society is, what percentage does it need to be before you believe the scientists? And that's what I would say to Congress. And so I think if Congress understood that the science is not as complicated as they think, and it's virtually settled, and say, all right, let's get beyond that. Let's accept what the scientists are telling us, and let's just debate and come together and decide what are we going to do about it. I think that would be the only way that we can get them to do anything there. And actually, I have a policy recommendation that's too long to share with you here, that I think both political parties would actually accept and would actually help. And I'm going to formulate that into writing. I've been thinking about it for a couple of years, and I'm going to submit that to one of my senators and have them present that, because I've bounced it off of both. I've bounced it off of people that are more liberal than Bernie Sanders and people that are more conservative than Rush Limbaugh, and both of them have said, yeah, I could work with that. So I think there's some hope there. And so I'm going to try and get that presented to some of our senators and see what happens. All right, we have lots of other questions here. Let's see. What is the effect of melting of glacier and ice in Earth's ability to radiate back incoming solar energy? Great question, because ice is highly reflective. So when you have that polar ice, you're reflecting solar radiation back out to space. When you melt that ice, you're replacing it with ocean water. Ocean water is darker, and that's absorbing solar radiation. So yes, it's called a feedback loop. What's happening is you're with less ice, you're actually increasing the warming at the pole, because the water is actually getting warmer, because that absorbs more solar radiation than what would be there if you had the ice cap, which would reflect more of that radiation. So that is a very valid point. The albedo, if you will, the surface albedo of the pole is very important. All right, next question. Why is methane more potent than the CO2 and NOx? Boy, I don't know the chemistry as well as some of you guys, but it's something that I've been taught and that has been told to me by climate scientists for many, many, many years now. And I can't remember the exact chemistry as to why. And I feel like I should, but I have not ever been asked that question. And so I can't remember why. It's chemistry. And I apologize. I just don't remember the chemical answer. It's chemistry, but why?
I think it's an inherent property of those molecules having to do with their thermal properties. I don't know the name of the property. Don't forget that top question there.
Yeah,
Paul.
I just saw it. And what are the top mitigation strategies in your opinion? Now, when you say mitigation, I'm hoping that you mean what can we do in order to mitigate some of the impacts of the warming. So let me just share with you what's happening in South Florida, in Miami's Dade County. Dade County is the county that includes Miami. They decided years ago, we can't wait for the federal government. They're not doing anything. So they created their own climate change mitigation task force, a government level task force in the county government. And they are looking at all the things that they need to do to try and mitigate some of the changes due to the warming of the climate. So things like, for example, like right now, you know about the tides, based on the moon's orbit around the earth and all. I mean, tides go up, tides go down. Well, there's something called king tide. And king tide is when high tide comes at the same time as a full moon or a new moon. Okay? So when you have king tide, okay, that's a higher than normal tide. And right now, and this didn't happen in the past, but right now in Miami, if you get a king tide, it's just routinely flooding areas now. There are streets, water is coming down streets now due to a routine king tide. If you get a hurricane with higher sea levels, your storm surge is going to push farther inland. Things like that. So they're working on things that can mitigate some of those impacts from the warming. And keep in mind that when you push ocean water inland with a hurricane, That's salt water. That's brackish water. That's water that will kill freshwater farms, plants on farms and things. So the farther inland, it's not just a flooding people thing, but it's also flooding farms and things that are inland with that ocean water. So there are lots of places around the country that are looking at things that they need to do to mitigate the impacts of the warming. Here in the Great Lakes, we're seeing it's not all attributable to climate change. So I'm not attributing it to climate change, because there is a cycle of Great Lakes water levels. We're at record high levels right now, and it's going to continue record high for the next few months. Every storm we get here with any kind of wind is pushing a lot of water and wave action into shorelines that are getting flooded and with damage now. And so on a larger scale, with our ocean coastline areas, they've got to be looking at things like that. So mitigation are things that communities are doing, because it's not happening with the federal government. It's what are communities doing to try and mitigate some of those impacts. Let's see if there are any more questions here. I got to put my glasses on.
I will say too, Paul, there is a bill, I guess, I'm not an expert on this. I'm just informing people so they can look into it to greater detail. There's a bill in the House right now, I think, that's being put forward on, having carbon exchanges to help lower carbon dioxide. And there's a group called the Citizens Climate Lobby, CCL. You can Google it, and they are the ones that are backing this bill. It's mostly got Democratic support, but there is one Republican in the state of Florida who is, because of the reasons you've just talked about, who isn't in favor of it. So I would encourage people who are interested in it to look more into that to see what can be done. And I'm sure there's letter writing campaigns. And
some of the things that have been proposed by the Democrats are too radical as well. And that's why we need bipartisan. We need these congressmen and women and the senators to come together in a bipartisan way, accept the science, and say, okay, what can we do together to come up with something that we can both accept to do something with this problem? And so it has to be bipartisan. We've seen, I'm not going to start getting into politics with past stuff, but we've seen just in the recent years, when things happen in a partisan way, they usually are not done right. They've got to be done bipartisan. This has to be something where everybody recognizes that. And listen, if you talk to any top military commander, they'll tell you climate change is a national security issue. They will tell you that, rising sea levels in our naval ports and things, just one thing. So what is another question came in? Is there considerations about black carbon? Well, I already mentioned about aerosols and soot. And so they're doing research into aerosols and what impact those are having on the warming. So that's just one of those gaps that we're trying to get a better handle on right now.
Anything else by any of the other attendees? Don't forget, there will be a survey after the end of the seminar. So we hope you will hang out until that shows up and then give us some feedback on the talk. Any other questions?
If there's no other questions, I want to say one last thing, which kind of will wrap this up in kind of a nice way. And it's a good way to try and explain everything I've just showed you into something real nice and easy and understandable. And that gives you an ability to explain it to other people. And if you're any kind of a Major League Baseball fan, you know what I'm talking about when I tell you about what happened with steroids in the past 3 decades. Okay. Back in the 1990s, you had some guys hitting home runs and doing things that had not been seen in decades. And it's because they were taking steroids. And so with these baseball players that were taking steroids, they were great hitters before they took steroids. They were hitting lots of home runs before they took steroids. But what the steroids did is some of the balls they hit went farther. And so a ball that might have been caught against the wall or on the warning track, if it goes only 5 or 10 feet farther, that's now a home run. So all of a sudden, these guys were hitting more home runs. The home runs that were going to be home runs anyway, those were going farther. And then the ones that were marginal were going farther as well. And so you were seeing an increase in the number of home runs they were hitting. So by increasing the gases in the atmosphere, what we've done is we've basically put the atmosphere on steroids. Yes, we've had tornadoes and big tornado outbreaks in the past. Yes, we've had hurricanes and bad ones in the past. We've had heat waves, we've had droughts, we've had flooding rains, we've had all of this in the past. But what we're doing is putting the atmosphere on steroids. And so what's happening is these extreme weather events are becoming more common now, okay? It's not that they didn't happen before, it's that they're happening more now. And so that's a really good way to understand this, that the increase in greenhouse gases has put the atmosphere on steroids, and we're basically juicing the atmosphere and giving the atmosphere a more predisposed method of creating a more high-end weather event. So, and another question just popped in. Let me put my glasses on again. What do I think about new energy sources like electric cars, solar energy to combat and control emissions? I actually just 3 months ago leased a Chevy Bolt. I've gone all electric. I tell you, by the way, it's a lot of fun to drive. It's great fun. I haven't been to a gas station since January. Now, some people say, well, listen, if you're using, you're plugging your car in and you're using electricity to power the car and charge the battery, well, obviously that power generation has to produce some greenhouse gases too. But still, the benefit of not having a combustion engine, so not burning gas, is still much better. The benefit of not doing that is still much better than the extra electricity you're using to charge your car. So yeah, that charging an electric car and solar energy are all part of the solution. Those things can all help. Anything that reduces power use or burning of fossil fuels is a big positive. Any of those things can really help. They can't by themselves do it, but as part of an overall global solution to a global warming, yes, those can be very beneficial parts of the solution.
I would also encourage that questioner to, when the link becomes available, to check out the talk that we had on Monday, because that speaker spoke to renewable energy sources and their impacts, so economic and otherwise. So you might find some more information there once that link gets posted. Peter Sinclair's talk. Thanks a lot, Paul. We really appreciate it, and thanks to all those who linked in today.
Well, I appreciate the opportunity. I love talking about this stuff. I'm not an advocate, just want to teach you about the science. I'm really, really appreciative of the opportunity to be able to educate all of you.